All right, let's get started. So next week, we have class on Tuesday. The homework's not due next week. It's due the week after that. So I'm still working out what to do about the last homework. I do want to give you enough time to do it, clearly, and not have to do it right before the final exam. However, we are short weeks, so I will let you know. The worst that will come of it is that we'll just have the homework due a week beforehand, but you'll still have some time to study for the exam and things like that. Are there any questions otherwise before we get started? Okay, so I don't exactly know where Professor Spiegelman left off. He said he got through some of QR factorization. Is that true? Did he get to Gram-Schmidt? No? Okay. Well, let's go through QR factorization really quick. These are the general ideas. The basic idea is we want to break up A into different spaces. So we want to use the columns of A to actually span the space, the column space, and we want to have some representation of the successive spaces that are indicated there. So we kind of have this idea that as we keep on adding columns, the space that each of the columns is spanning is going to be contained in the columns before it, of course. But we want to try to come up with an orthonormal basis for those spaces. So that we want to have, in the end, some other set of vectors that spans the same space. Okay, so hopefully these vectors are nicer. Usually we do want them to be have some sort of properties. So the basic idea here is that we're going to just construct this iteratively, starting with vector, the left column of A. And actually, you don't have to start there. It's just what we always do. But the first thing we want to do is just take Q1. We're going to make it equal to the first column and then normalize it. So everything else after this needs to be orthogonal to this first column. And that's how we go about doing this. The second column, we take A2. We subtract off the vector that's in the direction of Q1, so that once we do this, we no longer have any part in the direction of Q1. We normalize that vector, and we call it Q2. And we keep on doing this. You can show that once we do define it this way, that, of course, Q1 and Q2 are going to be orthogonal to each other and also orthonormal. And we can go about this, and we can write then in the end the QR factorization where A, the entire matrix A is equal to some matrix Q times a matrix R, which is upper triangular. The way we actually determine what these things are, as you can see, A1 has to be equal to R1 Q1 just by matrix multiplication. And so we know then we can basically identify what R11 is because of that. So really, R is telling you how to construct a matrix A in terms of the orthonormal basis Q. Okay? So that's one way to interpret this. But we can actually go through and say, all right, well, R11 is going to be the normalization. R22 is going to be basically the normalization, but with the component in the Q1 direction subtracted out, and then we can keep on going down the diagonal. And then the off-diagonal cases are going to be the projections into each of those directions. So in some sense, you can kind of look at like R12, the off-diagonal pieces, as the direction of the columns of A in each of the first Q values. And also that's why then R ends up being upper triangular. Okay, so that's the basic idea. We want to construct something Q times R that's going to give us back A. Q has to have orthogonal columns or orthonormal columns, and R is going to give us back the matrix A. So that's our goal. Probably the most straightforward way to do this is Gram-Schmidt orthogonalization, which we were basically just doing. So we want to subtract off the components of the vector Aj in the direction of QI vectors. Okay, so in an algorithmic sense, if we're trying to figure out the Vj, so Vj is going to be a temporary vector in this kind of notation. And we're going to say Vj is going to be equal to Aj minus all the components of all the Qj's we've already formed. So that's why we're going all the way up to Qj minus 1, subtracting off the projection of Aj onto all those Q's. We can just write that simply is this sum here, and then we normalize it. Okay? So that's just describing algorithmically for the jth column of A, how do we get back out Qj, like that. All right, so just like before, we can actually figure out what the R's have to be from this. If we say, well, we know R11 times Q1 has got to be equal to A1, because that's just multiplication of Q and R. We then can say, well, Q1 has got to be equal to A1 over R11, like that. And we can start to say, okay, so what are these R values again? And we can write the generic values of them as the projections in Qi and Qj, or excuse me, Qi in the ajth column, and then the normalization that we used before. Okay, so that's Gram-Schmidt, classical Gram-Schmidt. All right, so hopefully this isn't particularly new. Hopefully you've seen it in linear algebra. Maybe not. We're going to talk about it more in a computational sense. But this is something that hopefully you've at least seen once or twice before that way. But the first thing we want to do is actually try to do this in code. So I want to give you a couple minutes. If you don't remember Gram-Schmidt, remind yourself, or try to write it in code in this case. And I'll make some comments along the way. And we're going to come back to this in a few different ways on how to compute this. Note that once you find a QR factorization, we have some statements that are going to suggest this is unique. So regardless of what algorithm you use to find them, hopefully it'll give you something back that's always unique in certain cases. But we're going to find out that this isn't actually a very good idea. So, and we'll discuss a little bit about that once we get going. Okay, so I'll give you a couple minutes for that, and we'll code it up after. All right, let's kind of reason our way through this. Classical Gram-Schmidt is really taking the equations we have up above, figuring out what indices to use, and just applying them correctly. So let's try to do that. I'm going to make this a little bit bigger. I have no idea why this screen is wrong colored. I tried to reset it and it did not work. Anyway, the first thing we're going to do in this particular case is we're going to form to the two matrices we want to output, which is Q and R, and we're going to just make R be all zeros because we don't need to touch the lower corner of R, so we're just going to fill those with zeros and fill in R as we go. And R is n by n. And I'm going to make an empty Q because we have to touch every single value in Q, so we can not worry about filling it in. So Q is going to be m by n, just like the matrix A. Okay, so the outer loop is going to be going over each of the columns of A. So we're going to start with the leftmost column and go all the way to the right. So that's going to be a for loop for j in range n. Okay, there's n columns. We're going to use j because that's actually the notation we were using before. So we're going to be working inside of this loop on the jth column as we go of A. So then we're going to grab what the jth column is. We're going to store it in V just for the time being. So this is, again, trying to get, if we go back up here, we're going to calculate it this way. And then we're going to use Vj and just normalize it to give us back Q. So here we're getting the A. And then I'm going to say for I in range j. So now we're going to start working on each of the values inside of the arrays. Oh, one other thing. So we're going to start subtracting off everything we've done before. So the first one had best not do anything, which is going to be true since if the range of range from j is equal to 0, we're going to get back nothing. And we just want to make sure that that works. But if we're working on the jth column, we know that each of the Rij's that are not on the diagonal, that's important, is going to be the inner product between all the other Q's. We're just going to use conjugate just because if we did want to do this with complex numbers, we'd have to use that. In our column A. Okay? And we're actually going to grab the A column instead of using V because V we're going to change as we go. So here we're going to say V is V minus Rij times Q I, like that. Okay. So that's just giving us basically the V as we're calculating it up here, like this. And we're going to start taking values from that R as we compute them. So we're not going to recompute all the inner products as we go, like that. Okay, so now actually we've done all of the subtraction off from each of the directions we've already computed, all the Q vectors. We still need to do the diagonal value of R, but that's just the norm. And in this case, we were just doing the 2 norm. Okay, so that gives us R, and then we can just form the current vector j, qj, is V divided by that norm, like that. Okay, so that's taking into account computing all of these things, subtracting them off like we were supposed to, and then dividing through by that the eventual vector V that has everything subtracted off from the Q columns before it. So if we run this, there's a few tests here. Just prints out A and Q. Then I'm going to take Q dot transpose or Q dot conjugate times Q, which should give me back the identity, because this is a unitary or orthonormal matrix. It is its own inverse, or its transpose is its inverse. So you can see we have this matrix here. We have 10 to the negative 17s off the main diagonal and 1s down the diagonal. So that's a pretty good approximation to that. Here we have Q, which, I don't know, they look like they might be orthonormal. There's no way really to tell from this. Here's the matrix R. It looks all nice. interestingly. And then we have the difference between Q times R minus A. So we would want this to be zeros. And it's mostly 0. There's some 10 to the negative 15s, some 10 to the negative 14s in there. So not exactly as well as we might want to do, but it's pretty good. Okay. So this works. This isn't a particularly difficult matrix to do. We can actually create matrices that this doesn't work very well on, even though the mathematics is the same. But let's think about that a little bit. So first off, we can say that there is a QR factorization for any A. We just have to define it carefully. So in this case, what we'll do is we'll say, well, A is going to have some QR factorization where the normal one would be Q1 and R1. Okay, and that gives you back A. But then if we have A not being square, we can have all sorts of things happen. Right? So if you're thinking of the matrix A mapping well, Rm or Cm to Rn or Cn, right? Those are two different spaces, it could be different sizes, then this other, so this is going to have to span that space, the column space of A, but there's more space in there on the right-hand side, and this has got to span that then. Okay? So that's just taking into account that the two spaces might not be the same size. Q2 times 0 just means that Q2, A has no ability to get into this space here, whatever space that this is spanning. So we end up getting Q1 times R1 is equal to A still, but we can actually use these Q2s to figure out what's going on in the rest of that space, just in case we want it. So we call this QR factorization the reduced or thin QR factorization of A, just meaning that it's, this rest of this stuff isn't actually used very much. And also, if you know what this rest of the space is, you can actually construct this pretty quickly. But the full Q1, Q2 will be available to you if you want it. All right. So there's a couple different things we do kind of care about here. One is that every A with m greater than or equal to n, so that is one case we do need those dimensions to have a relationship. Each of those has a full QR factorization and therefore a reduced QR factorization. So that's just saying that one space is bigger than the other, or they're the equal, in which case you have the reduced and the full equaling each other. This one, the second comment here is a bit more important, and that's just that if A is a full rank, it has a unique reduced QR factorization. Okay? So that's just saying that you can actually characterize the matrix A with its orthonormal column space basis and that matrix R. All right, so it shouldn't be too surprising. We can come up with some sort of set of columns or set of vectors that are going to span the space that A is mapping between. Since it's full rank, we know we can get to this space. And if we're just thinking of how we're going to project each of the columns of A into R, it's just changing or rotating how we're actually thinking about mapping these things between each other. So this is hopefully not too surprising, but it is actually important, and we will definitely use that as we continue on. These aren't too hard to prove. If you are interested, I can show you after class how to do that. Okay, so we talked about projections a bunch, or we didn't. You did with Professor Spiegelman. So we're actually going to go back to using projections in this sense. So we're going to rewrite the classical Gram-Schmidt as a series of projections. So in this case, the projections are going to be basically the projections onto the Qs all up to the one that I'm on. And all I really want to do with this statement is that I want to just view it as a projection. So it's not changing the algorithm or what we're doing. We just want to know what these P's are for this. And note that the projection then should therefore actually project onto the rest of the space that we haven't spanned by the Qs up until that point. That makes sense. That's why we're subtracting off. We're projecting onto the complement of the space that the Qs already span up to the column that I'm interested in. Okay? So that statement is kind of important for everything else we're going to do. So think about it. Think about how you'd actually construct these things. So the kind of picture in my mind here is that we have Q1, Q2, Q3, all the way up to Qj minus 1. Right? We're trying to construct Qj so that it's orthogonal to all these other things. So want Qj. So what kind of projection is that? How do you construct the projection that's going to give me that? Don't worry about the normalization. That just kind of comes for free. But what do these P's are? What's the Pj projection? So I'm going to give you a couple of minutes to think about that. Talk it over with your neighbors. It's something, it's a projection. You have to use the Q's some way, shape, or form. And think about what the projection actually looks like. Okay? So I'll give you a couple of minutes for that. Okay, so this is the idea. We are going to construct these this projection based on the fact that we already know these are all orthonormal. So we can go back to this and say, all right, so if we have Q, the matrix with these as its columns, if I do Q, Q star, we've already know that that's a projection matrix, and that's projecting into this space. But that's not the space we want. We want the complement of this space. We want this thing to be living in everything else. Okay? That's where the complement comes in. So we're basically, in some sense, eliminating the direction that Q or AJ is in each of this space. Okay, so we're taking AJ, we're turning it into QJ by removing that direction. That's where the complementary projection comes in. And then, to get that, we just do I, the identity, minus the original projection. Right? I minus P is going to give you the complement to the projection of P. And that's what we need to do here. So we have Q hat I minus 1. I don't know why I'm changing to I, but that's going to be formed from all the columns up to the column that we're trying to create. We're going to say that there's a projector P hat that's going to be Q hat times Q hat star. And then the actual projection we want is the complement to that thing, and we get this back out. Okay? So this is just a projection defined the way we had before. The hats are just so we can keep track of the fact that this isn't exactly the same thing. So how does this work? Oops. Did I say that more? I don't think so. So basically, once we've constructed all these projections, we can go about doing our business up here and just write all these out. So you still have to find the R's, but we know what the R's are. independently. So note that you wouldn't necessarily want to do this for if you were actually computing something. The way you want to compute classical Gram-Schmidt is the way we wrote it, where you're finding all the R's as you go. This way, you'd only find the Q's. You need to go back and find all the R's, and you'd be recomputing things that you already had basically done already. So this is useful analytically, though, to think about the method. OK. So there's something called modified Gram-Schmidt. Probably haven't heard of this, more than likely, just because from analytical linear algebra sense, you can stop where we just were. But from a numerical sense, we actually have to be a little bit more careful. So what we're going to do is think about how we might actually write an equivalent algorithm from a infinite precision case. But we can maybe make this a little bit better. And it has to do with these projections. So if we're going to take the inner product of aj with all the relevant qi's, so basically all the I less than j, there's problems that can come up. So if you want to think about this, if we're actually going to be subtracting off numbers, if those numbers are almost the same as a, we can get into trouble. We know that that could lead to catastrophic cancellation. What does that mean? Well, there's two things that can happen. One is that aj is actually basically almost all the way in to one of the spaces, so it's nearly parallel or nearly all the way into one of the spaces, or it's actually orthogonal to all the rest of the columns we've come to from before. That both of those cases will lead us to trouble. And that's completely arbitrary based on A. We don't know what's going to happen that way. So that's not great. The way we're going to talk about it here is it has to do with the rank of the projection. So the way we described the projections before, they're actually m minus I minus 1. Okay, so what is that? Well, it just means that when we're building these projections, we're only projecting on part of the space, the complement of the space. And as we keep on going up, we're actually projecting on a smaller and smaller space, leading to the rank that could actually be decreasing. Okay? It could be worse than this, but we don't know necessarily. And that's really the core of why classical Gram-Schmidt doesn't work so well. Instead, we can actually look at it a different way, where we're going to actually say, let's construct projections that are always going to be projecting on everything except the thing we want. So that's actually going to give us an m minus 1 rank projection, which is as good as we can do. We're always going to have to be doing that. And then we're going to construct the complement to that projection and perform a series of projections instead of just one, like we had before. OK, so we want to complement. This is the complementary space. We can talk about this as we go. But that's the key idea. And these do lead to different algorithms in these cases. But let's actually look at iteration. So we have vi1 is equal to ai. vi2 is equal to the projection, the complementary projection of q1 vi. So note that when we're doing this, we can actually just write this all out. But we're going to be doing it as we go. So we're always going to use this projection, right? So that was the big difference. The projector we had before was the complement of all the Q's all at the same time, whereas this is only one at a time. And we're going to always be using that projector as we go. So identical mathematically. We're doing exactly the same thing, but this is actually a bit more stable because we're actually making sure the space is as big as possible that we're mapping to. It is a full rank as possible. Okay? And we're going to iterate this. So we're actually going to keep track of the VIs as we go, and we're going to be subtracting them off one at a time. Doesn't mean we have a bunch of projectors that we're going to be forming, but we know that from a computational standpoint, we can just do this inner product and not have to worry about that part. Okay. So try to implement this. This is a little bit more complicated for obvious reasons, but it does lead to a better algorithm. So give it a whirl. See if you can convince yourself like what it is. I think probably the biggest thing here is understanding what a rank, like why are these projections higher rank than the last ones? Because that's really what's going on in the background here. And it'll come up when we talk about householder reflections as well. Okay? So I'll give you a couple minutes for that. We'll implement it, and then we'll go on to the next algorithm. I thought of another way to explain this. We'll see if this works a little bit better. Say we're in R3. We have a vector in R3. We're going to construct a projector that projects onto the, say, XY plane. Okay? What's the rank of that projector? So if I have this projector here, this is going to be in what? Ish. If it's projecting onto a plane. How many dimensions does the space that I'm projecting into have? 2, yes. So in some sense, this is R2, right? Its rank is 2. Could be less, but it's going to be 2 for our purposes here. So this projector is going to have m-1 rank. The other projector we could do is projecting into the one direction we don't want and then subtracting it off. Right? So if we have, well, so if we have I minus P1, that's actually going to project onto the complement of, say, the xy plane. But then I can also actually just subtract off this component in that direction. Okay? This projector here is rank 1. by the fact that we have to get back into R2 and R1. All right? So this is what the classical Gram-Schmidt is doing. We're actually forming a projector that's projecting into a much smaller space, especially as we keep on going. So the first projector is going to be nothing. It's projecting on it to itself. The second projector is going to be projecting into all the rest of the space that's available to it. So that's fine. It's going to be m minus I minus 1, or m minus j minus 1. Okay? But as we keep on going, we're going to start having more and more space that's being taken up by the rest of the columns of Q. So by the time we're getting towards the right end of the columns of A, we're projecting into a smaller and smaller space, which means the projectors have smaller and smaller rank. Whereas if we do the opposite, we actually always are projecting into something that's as big as possible. Right? There's only one direction that we're worrying about when we're doing that. Okay? Hopefully that helps a little bit. Maybe. I see puzzled stares. But think about it a little bit. Hopefully it will click. But let's implement this. So one of the big things here is we're actually going to keep track. We have to make a copy of A. Because if you look up here, what we're really doing here is actually we're going to be modifying all the V's all at the same time as we go. That's the flip here. We do need to keep track of them all. So easiest thing to do is copy A. One thing of note for this homework assignment and the next, if things are going haywire and it seems odd what's going on, try copying things. That tends to be a key to this. It just means that, so Python has this strange thing where if you're starting to modify, if you do this and you didn't do the copy, V is going to be equal to A. If you start modifying V, it could modify A, which you're going to be very unhappy about when you get back out of the function, because everything's going to be weird. So copy actually makes a true copy of A, so you could modify V without modifying A at the same time. Okay? So just be aware, if weird things are happening, try some copies. We're not going to take off points if you ended up copying things you didn't need to, but it can be frustrating in the meantime. Okay, so matching my notation above, we're going to do, if I can type, because for some odd reason I changed I and j. For I in range n, and then at this point in the loop, actually, I already have computed the ith column completely. It's already been done for us. We don't have to actually go through and subtract off the values of the vector. So at this point in the loop, I can already compute what the norm of this thing is. Okay, so basically VI is already done. We've already completed everything we need to do with VI, that column. And then consequently, we can actually store it in Q. Like that. Okay. Now, if that's the ith column, now I have to compute all the subtractions from the ith column over to the right. That's the rest of this algorithm. So everything, not I, we've already done I. We're going to do everything from I plus 1 to the end, like that. So that's why this has this. I'm going to compute all the rest of the ij's, or the r's, excuse me. So those, again, are going to be the inner products. Okay. Now, we're going to be doing this for all the v's, again, to the right. So we're going to subtract off what we've already have up to this point. And note that it's only going to be qi. So qi is always going to be the same vector. It's the vj's that are changing. And then I do the same thing. I subtract off this component, like so. Okay. So that's actually the same step as before. We're just rearranging in the order that we're doing things is really what's happening here. And then we're done, I think. I did not do something right. Oh, that's right. Oops. Which one? Oh, this one? Oh, yeah, you're right. Yeah, thank you. So here we go. We see that the difference between the Q times R minus A is about 0. We have the identity matrix again, and we see we have R and A, and everything is working. We're getting basically the same answer out from before. Okay. So how many of you have seen householder triangularization before? No one? Okay. Well, yay! So this is another way to do the exact same thing, yet again. It just happens to be a really good way to do it. And there's actually some nice things beyond householder triangularization. Excuse me, we're going to use householder triangularization again to do other things. So bear with me. This seems needlessly complex, but it will be nice to have. Okay, so another interpretation of Gram-Schmidt. If we wanted to say that Gram-Schmidt was actually a series of multiplications of the matrix A that gives you the matrix Q. So we have the matrix A here. So we're just saying the columns are V because that matches what their algorithm is doing. This is the matrix A. We're asking what matrix R-ish here is going to give me an orthonormal column in the first entry. Okay, so A times some matrix R is going to give me one piece of my orthogonalization. Okay? And that's actually what we can do. We can kind of retask this. This is clearly not R, because if R11, which is actually R11 that we want, if it's 1 over R11, that's definitely not R. In fact, that's going to be some sort of inverse of what a piece of R. Okay? But this is a nice way to look at things. We can continue to actually perform these steps like we did for the modified Gram-Schmidt. So we're taking the rest of these components, so basically subtracting off the components in each of the directions of the rest of the values. So it actually gives us a row in R. And what that's going to do is it's going to give us the V2, V3, all the way to Vn that we had in our modified Gram-Schmidt. So this is just, these are slightly modified vectors such that I've basically subtracted off Q1, the components in Q1's direction from these. Okay? So this is actually one step, one of those outer loops of modified Gram-Schmidt. You have this matrix modifying A such that I get that. Okay? And I can continue. Okay? So the second one, so we're going to call that thing R1, that matrix on the left-hand side. We're taking A again, just A by itself. We're multiplying by R1. It gives us the last matrix we saw. And we're going to do it again. We're going to construct another R such that it gives us Q1 and Q2. And then we have the slightly modified versions of V. Okay? So you can probably guess at this point what's going to happen. What we're going to do is continue until we have everything. So we have R1 through Rn. If we take the inverse of that matrix, we're going to get back something that looks more like R, and we're actually done at that point. Okay? So we can actually do all of modified Gram-Schmidt this way. We just have to figure out what those R's are. And then if we wanted to get R back out, then we can just take the inverse of that matrix. It's upper triangular, so it has some nice, it's not as bad as it seems. There are actually reasons not to do that. Sometimes you want R inverse. So kind of depends on what you want to use that for. That's just another way to look at modified Gram-Schmidt. Okay, so that's great. Oftentimes we call this Gram-Schmidt triangularization. Really, this is just saying we're trying to take the matrix A and transform it into something else. Okay, so not super useful for Gram-Schmidt. It's like, you know, it's just a different interpretation. All right, but there is another thing called householder triangularization, which has the same idea except it's slightly modified. What we're going to do is we're going to say we want to construct a series of Qs that take A and make it equal to R. Okay? The reason why I call this triangularization is that R is upper triangular. So we're trying to find the sequence of matrices multiply them by A that turns A into an upper triangular matrix. And of course, the Qs are going to have a relationship to the Q we're always looking for, and we can actually, if you say Qn through Q1 is equal to Q star, then we know actually the Q that we really wanted, because these are all unitary matrices, we can get back out exactly what we want. And these are all, these are just transposes, so these are easier operations to do. But this view of this algorithm is such that we actually can construct things in R, to make R. All right, so how does this work? Well, so this is just the kind of the complementary. If you just do this in sequence, you take Qn star times Qn on both sides, you end up slowly moving everything over. Note that this is actually reversed. So it's Q1 star through Qn star, and then this is Qn to Q1. Doesn't really matter which way, you just have to realize that things need to be flipped in direction. So that actually gives us back A is equal to QR, if we can do this. Okay, so just to kind of give just a diagram of what's going on, we have our matrix A. Q1 is going to transform the matrix A so that it's going to be, so Q1 times A is going to have zeros below the main diagonal, and everything else we don't care about so far. Okay? Q2 is going to take this matrix and remove the values here and make this zeros below the diagonal, and Q3 is going to complete it. So this would be the matrix R, whatever's up above, but Q1, Q2, Q3 are going to have these actions. So what we're really looking at now is that these Qs are going to be removing zeros below the diagonal, these matrices. Okay? So how does that work? Well, we're going to construct a projection or a matrix of this form. It's going to have the identity in the upper left-hand corner. So this is a block matrix. So this could be 10 by 10. The top left-hand corner is going to be an identity, however big that is. And then we have this F thing. Okay? Why we do that? Well, it's because once we've gotten these zeros below the diagonal, we do not want to touch that. We want to leave those alone. So the identity is going to help us with that. We're saying, do not do anything with the columns to the left. Just worry about the rest of this matrix. Okay? Same thing here. Once we get these zeros, we don't want to pollute any of the stuff over here. So the identity would be 2 by 2 in this case. So it's going to leave everything below the diagonal alone for us. Okay? Now, it still doesn't really answer the question of how in the world do you do this. So let's actually try to figure this out. And note here, we're just talking about F. And F is going to be working on a smaller space, too. Okay, so we have the identity, and we have F is going to take up the rest of the space. So these two things have to be complementary in terms of their sizes. Okay, so now we're going to talk about householder reflectors. So a reflector is basically taking, say, a vector x, okay, and flipping it over some plane. Okay? We're going to say that's an arbitrary plane at this point. But if we have something like this, we have a vector going to x, I want to get the vector v back out. Okay? So it's not just projection onto the plane, it's actually projection plus some extra stuff there. Okay? Actually twice. Right? The distance between x and v is the distance between x and the plane times 2. So keep that in the back of your mind. This householder reflector, okay, well, this isn't the householder reflector yet. This is just an arbitrary plane. But you can see what might be useful here. By choosing this reflector, this plane, very carefully, I'm reflecting it back onto the x-axis here, which means I've actually removed the direction in the y direction. Right? So that's the idea. We're going to find these reflectors such that they're going to be projections onto lower dimensional subspaces. Okay, so keep this kind of picture in mind. We're going to be doing it in n dimensions, so sorry about that, but that's the basic idea. So down here, what we really want F to do, it's going to take a vector x, and I want it to actually remove all the values in all the other directions except for the first one, and I want that first one, that value to actually have the original vector x's value in it. And that's actually exactly what's going on here, just for 2D in this case. Okay, I'm removing all the values. This is going to have the same magnitude as the original vector x in only its first component. Okay. Now, we're using E1 here. This is just going to be the unit vector in the E1 direction, because this is clearly not a vector. Note that this is f. So this is working on a subspace. So again, once we've actually computed the q's or the r's and gotten rid of all those dimensions, we're only going to be projecting onto the smaller space as we go. Okay? So this is actually very a common type of linear algebra idea. You work dimension by dimension so that every single time you go through an iteration, you're actually working on a smaller and smaller and smaller space or problem. So that actually makes it faster, and it makes it easier to construct and understand convergence properties and error, and you're living in a smaller space, which is not good if you have a small apartment, but in mathematical terms, we actually like that. So that is the major idea here. Okay. Well, that looked like a projection quite a bit. It's not a projection so much, but it looks like one. So if we're going to say we have some projection P, okay? And we're going to say V is going to be equal to the vector we want, kind of this xe1, minus x, though. So it's not the vector we actually want. It's the vector that has the component subtracted off from it. So we have px. We know because this is some form of a projection itself, and this is the complementary projector, which gives me that thing up there. That's what we formed here. Okay, so that's projecting in the complementary direction of v in this case. And if I just carry this through, I get x minus x times that original projection. Okay, so projection in the v direction, normalized it. It's still in the x direction, and then we have x there. Okay. Well, that's nice. It's a projection. But note, this only gets me in this direction. Right? Actually, it's going to give me this thing. So that's going to be orthogonal to whatever I want to do. Okay? But if I go and say, all right, so that's going to be subtracting off a certain amount of v. If I go twice that far, so again, if the original one gets me here, and I want to go all the way over here, I multiply by 2 the distance I'm going to change the vector by, and I get this. So this is for the plane that I'm going to be projecting onto. This is going to actually give me the reflection instead. I'm going twice as far as I should, and that's how I get there. All right, so that's a reflector. They always have this type of look to them. You pick a direction that you're going to be reflecting around, and then you go twice as far as you're supposed to, like that. So it has a feeling of a projection, but it goes a little too far. All right, so well, there's some issues with this. There's actually a non-uniqueness to this direction. We can actually pick 2 different directions. By convention, generally, we choose the sign to be x1 times this plus x. So this is the v vector. So going back here, call that the v vector was defined as the vector we wanted minus x, which is this thing here. All right? So we're projecting onto that. The thing is, we can actually go both sides, and we can actually rotate this by 90 degrees and still get something else out that works. So that's why we have this particular convention for the direction. And this is defining then how we are constructing this matrix F. All right. So you have a couple of minutes. See if you can convince yourself that what I just described is an actual thing that's actually reflecting along that plane, that in particular, this is something we want to do. Perhaps not, I don't know. Or try to actually implement this or understand the code. So we're going to implement the code, and this is somewhat useful to see, kind of walk through the algorithm. It's very, very direct in terms of the way we do some of the constructions. But give it a whirl and come back and then talk about why you may want to use one of these more than the other. Yeah? The reflection does, well, it's not that it's projecting onto something. It's not projecting onto a smaller space, but it is living in a smaller space by the fact that you've eliminated all the zeros. All right, so the key to this, reminding me about that. The key to this, note that, is that f is going to actually be removing all the zeros below the vector, which means that whatever action f is taking on that column that we wanted, it's going to have the magnitude of x, which, you know, is something we want, in r along the diagonal, and zeros below it. So this is exactly the thing we're trying to do. This is actually performing the triangularization for us. I'll leave that picture up. Okay, just to reiterate again, what we're doing is looking at, this is the complementary projector to projecting in the direction of V, which, if we go back here, is going to be something that's going to be orthogonal to this. So we're going to project, originally, that I minus V, V star business is projecting onto the hyperplane there, H. And then that's why we're taking 2 times that, because that's going to give us the projection onto V itself, like that. But let's actually try to implement this. Okay, so here you can see we're going to actually copy A into R. So again, we're basically asking the question, well, how do we change A into an upper triangular matrix? So that's what we're going to do there. V's are going to be empty to begin with, but we're going to fill them in as we go. We have the shape. So for K in range N, we're going to start with by constructing and kind of pulling apart R. Okay, so R we're modifying as we go. It's going to be the iterations. This is going to give me a piece of R. It's going to be a single column, and this is the column we're going to actually change by doing this. Well, it's more than a column. Wait, no, it's column K and onwards down. And it's the kth column that way. So we're going to construct a unit vector that's the same size as X. So X, again, is smaller than the rest of the matrix. It's whatever the subspace we're kind of working in at this point is. E1. Oops. It's going to be 1. So that's the definition of the unit vector. Everything else is zeros. And then I'm going to take and modify VK colon K. So this is actually going to give me the direction of that piece there. So this is just implementing this piece. So numpy.sign of x0 times the norm of x. Okay, so that's the direction, that's V. Let's construct that for my transformation. I then modify this a little bit. That. So basically just normalizing it at this point. And then I replace the rest of the R values and update R. So I'm actually, now you can see I'm working on the lower K by K values of R. Time. Oh, good. And that's going to be this operation here. We're going to multiply that by that. So we get 2 times the dot product of the outer product. So again, the outer product is VV star. That's the same thing. So that actually gives us a matrix. And that's going to be of V. And we're not going to worry about the conjugate transpose in this case. And that's going to act on this column here. So there's a lot of things going on in place. We're constructing R as we go, where every single time we remove a bunch of zeros from R, we also have to act on the rest of the matrix R as well. So the identity grows in the corner, but we're just leaving that out. We're only multiplying by the part of the matrix R we have to. I'm keeping track of the V's. You don't have to. But if you want the Q, you do. You need to do that. So this is actually just going to give you R. You don't actually have to construct or keep track of the Q's, but we're going to do that because it is good to do that. So we still have the same thing. Initialize Q as an empty matrix. Theoretically, we could probably fit, there is a way to actually do this as you go in the upper loop. It's just convoluted, unfortunately. But we know that we can actually construct these things by counting backwards. Second type. So here we're doing the dot product. Actually, I was going to copy this part, change some indices. Oh, I actually want this. Okay. So we're really going backwards and trying to reconstruct what this Q is based on the fact we already know what R is. We get this, and then once we've done all those, then we can get back out Q, which is just going to be this vector En. Okay. So that you can derive just from knowing what R is and knowing what the Q's need to be. So hopefully I typed this in right. I did not. This one's more complicated to debug. Oh. There we go. I think it worked this time. Oh, no. That worked. Oh, I guess I'm not checking that. Oh. I think it's working. We're getting zeros for the factorization at least. Okay. The business about reforming Q comes from this. We often don't actually have to form Q. You only need Q in certain circumstances. But what you can do instead is you can actually, like in this case where you're solving a system of linear equations, if you replace A with the QR factorization, you multiply both sides by Q star. This is an upper triangular matrix. This is just back substitution at this point. And then Q star times B, we know that that's going to be some sort of projection onto the column space of A. Okay. So that's kind of the idea. It's not quite the projection, I shouldn't say that. It's taking it in representing it as the column, in the column space of A. So there's all sorts of reasons why we may not want to form Q directly. We do need to do various things, and especially if this is the thing that we're going to try to do eventually. Oftentimes we can actually store Q in smaller pieces as well. Okay. So then this is what I did to form the Qs. I can actually get back, find the matrices F that we were constructing, and invert for basically the thing that I want, the directions of the VSs. Okay, so we've talked about 3 different algorithms. I've said that one of them is no good, and 2 of them are okay. But is that true? Well, here's an example where we can see it very clearly. We have a matrix A. It has a random eigenspace, so I don't know what it is. But I have said that the eigenvalues are going to be very disparate, so they're going to be far apart. The values along the diagonal of R gives us some idea of the projections. So the R, if you recall, is on the diagonal is just the magnitude of the normalizations. So as these get smaller, as these values get smaller, it means that we're projecting more and more of what the columns of A are doing into these directions. So if we go back here and look at this code, I have a random matrix, and I'm just going to QR it. So all this stuff is actually just constructing exactly what I just described. I'm actually using QR to do this, and then I'm taking and adding basically eigenvalues that are going to be very far apart, which is what this is really doing. Now I'm going to use all of my 3 methods, and I'm going to plot the diagonal of R. Okay, so let's just look what this looks like. Okay, so the blue dots are classic. These are the values of R along the diagonal. So that's why this is up to the index. And modified householder are down here. So what this is really saying is that at some point, I end up actually not projecting into these dimensions anymore, whereas this is actually, we see we're actually doing a bit better that way. This is down to 10 to the -16th. This stalls at around 10 to the -6th. Okay, so it's just, this has to do with how we're projecting each of these things into the space that we're constructing. Again, analytically, these are identical methodologies, algorithms, but due to floating point error and catastrophic cancellation, we can see things like this pop out. Okay, so oftentimes, this really comes up when you do have nearly columns of A that are almost linearly dependent on each other. That's really when this becomes an issue. And this is just an example of that type of thing. Almost kind of want to just finish. All right. We will quickly do this. Here's another example. So this is orthogonality. Note that these columns, these rows look almost identical except for that one down in the corner. So if we actually calculate this thing, you can see some differences in how we can actually go about doing this. So we're doing the QR factorization and then looking at whether or not these things are really actually unitary or they're orthonormal. And you can see there's some differences. So Schmidt actually is getting down to 10 to the -11th. They're not quite orthonormal, whereas Householder is getting down to 10 to the -16th. So that's why we actually use Householder in practice. There's actually other algorithmic operation count reasons as well. But you can also see that NumPy probably uses it, and it does. So let's stop there. I will see you next week. And all the TAs are moving their office hours around, so hopefully we'll figure that out. Otherwise, you wouldn't have any TA office hours next week. So.
I emailed you about the individual meeting today after class.
Yes, yeah.
So can I meet you in like 10 minutes?
Yeah, sure. I'll be downstairs.
Your
Office, yep.
Okay.
Hey. In the last homework, so I did the plot for all of them. Well, I didn't have this one in, obviously, but I was very interested in why these like stay bounded when the radius is 1, the magnitude is 1, and why these like just spiral outside. So these are the stability regions for Taylor series and Adams Rational arrays and remote state methods. Like if I but if I help it, it just fills more of the space outside that region. So I'm just wondering why that.
Oh, so we can plot R in these cases. There is no R for this multi-step. R was always we can't write R.
Okay.
That's kind of why. You can't actually do the people plot like this.
Okay.
So it's just more complicated. Are you just increasing like theta?
No, so this is just, so I always use all of theta. What I'm changing is the magnitude of the complex number.
Oh, so we always want A. So that's the thing, is like for the other methods, we just have to draw the one contour at these one. So eventually it should actually fill the entire plane. The value should be taken. So you're really just sweeping to the complex plane.
This means like they all come from like this like formulation right here, right? That like the so the same formulation. So that's why I was just thinking, okay, say we have like a full term like this, then like shouldn't both of them kind of convert like similar? I don't know. Maybe I'm not sure.
I mean,
what the question I'm going to ask.
These are definitely using RC, whereas this is kind of plotting something a little bit different.
I guess I'll look into it some more. Thanks. Oh, also, the thing that we were doing over summer, I still haven't got the net CDF file to run with. Yeah, I tried for a bit in summer and like